So let's try to grok completing the square. Try to figure out why does it make so much sense. So if I'm trying to solve a problem, let's say I have just simply, I have x squared equals 4. I mean, it's very easy to solve that problem. All we need to do is take a square root of both sides. We'll do that. Take a square root of x squared. Take a square root of 4. Remember our plus or minus. And so I have x is equal to plus or minus 2. That's pretty easy. It's really not much harder if we don't have a perfect square for our x squared equals. I have x squared equals 5. Well, again, I'll do the same thing. I'll take a square root of both sides, make sure I put in my plus or minus, and I wind up with x is equal to plus or minus the square root of 5. Nothing wrong with the square root of 5, a little irrational, but it's a perfectly good number. And it's really not even a whole lot different if I have a negative number. If I have x squared is equal to negative 3, do the same thing. Take the square root of both sides, put in my plus or minus, and I get x is equal to plus or minus I, square root of negative 1, radical 3. No big problem. Pretty simple. It's not even that much harder if I have a slightly more complicated term on the left-hand side of the equation. Let's say I have something like, x plus 2 squared is equal to 3. I follow the same process. Because all I have on the left side of my equation here is a perfect square, I can take the square root of it. I'll take the square root of that side, putting in my plus or minus. So I now have x plus 2, because x plus 2 squared, I take the square root of that, I'm left with x plus 2 is equal to plus or minus the square root of 3. And I think I'll just subtract 2 from both sides of this equation. And I get x is equal to negative 2 plus or minus the square root of 3. That makes it, that's not very complicated either. But in fact, getting to something really nice like this is what completing the square is all about. I use completing the square when I have something like, let's say x squared plus 3x minus 7 equals 0. So I have a quadratic. That's when we use completing the square. I have a quadratic right here. And this quadratic expression is unfactorable. And I can't just look at it and take the square root. There's no way to take the square root of x squared plus 3x minus 7. It's not a perfect square. So I want to find a way to be able to use this very simple square root method that we've been talking about to enable me to solve an unfactorable quadratic expression or a quadratic equation. What I want to do is I want to turn something in the form of ax squared plus bx plus c equals 0 that is unfactorable into something that is like x plus p squared that is factorable. I need to turn this, not that it's factorable, into this, so that I can take the square root and use this really easy method to solve a quadratic equation. So right here I use the letter p in this binomial squared to represent the constant that I'm going to have when I have my perfect square binomial. So I'm going to have something like x plus p times x plus p, that's the same thing as x plus p squared. Well, and I need to get that from ax squared plus bx plus c. How am I going to do that? Well, first of all, let's remember that when we're completing the square, the coefficient of our x squared has to be 1. So what I'm going to do right now is, rather than go and divide everything by a and make it look all weird, I'm just going to erase, whoops, I'm going to try to erase. Can I do that? Come on. I'm just going to erase the a altogether and figure that we've already done that. So I have x squared plus bx plus c. And I want to get that into x plus p squared. Well, whatever value I use for p has to solve two problems. One problem it has to solve is that p squared has to be equal to c. And why is that? It's because if I have, let's try to make this look right here, a little bit organized in our work. If I have x plus p squared, x plus p, and I'm going to FOIL this out to make it in the standard form right here, ax squared plus bx plus c, I can see that my last term, which is c, is going to have to be the same as p times p. Can you see that? This is going to turn out to be x squared plus px plus px plus p squared. And I'm going to be able to combine these two px's right here. So my first term is going to be my x squared, and my last term is going to be p squared, which is the same as c in the standard form. So rule number one, or condition number one, is that whatever I have for p in my squared binomial, whatever p squared is going to have to be equal to c. That's one thing that I'm going to have to make sure is true. Now the other thing that I'm going to have to make sure is true kind of comes from looking at here when I FOIL this out. This FOILs out to be x squared plus 2px plus p squared. So again, let's take a look at this 2p here, 2px, that has to be the same as the b. Well, that's kind of interesting. It's telling me that the 2p has to be equal to b. So if 2p must be equal to b, doesn't that mean that p has to be equal to b divided by 2? That looks pretty reasonable to me. If I want to end up with an answer that is double something, I take the thing that I want to end up with and I divide it by 2. So I've just done all this writing, and I've come to the conclusion that p squared has to be equal to the c when I write it out in the form of x squared plus bx plus c when I write it out as a trinomial. And I've also come to the conclusion that p is equal to b over 2. Now if you remember, when we're completing the square, what we generally start with when we're completing the square is an x squared plus bx plus blank. Let's take a look at it with our original example right way up here. This one right here. Let's see if I can't make that copy down to the bottom. So let's copy that, and let's bring it down to the bottom here. There we go. Okay. So I had this x squared, whoops, well, it looks like I can remove that altogether. Let's just do that. I had this x squared plus 3x minus 7. And you know that my first step after I get rid of my, my a and I have my coefficient of x squared as 1, is I like to move the constant over to the other side. I like to park it on the other side just to get it out of the way. So I wind up with x squared plus 3x plus blank is equal to 7 plus blank. And I put the two blanks on either side of the equation, so that's because I know that I'm going to have to, whatever I add to one side, I'm going to add to the other side. Well, we've just determined that whatever this is going to turn into in some kind of a binomial squared, we know we're going to have an x here to cover our x squared, but we don't know what this number here is going to be. We don't know what that number is going to be yet. Well, but we have some clues. We called it p above, but we know that that p is equal to b divided by 2, and that c is equal to p squared. So, if my c right here has to be p squared, and I know that p squared is b divided by 2, well, I have, let's write over here to the right here, different color. I have my b, which is 3, divided by 2, and then I'm going to square that. So that's going to be equal to 9 over 4. That means my c is 9 over 4, and I add it to that side. I'm going to add it to this side, 9 over 4. Now notice what's going to go over here. This was the p that I had, right? And the p that I had was that b over 2 was the 3 halves. So this 3 halves is going to fit right there. The whole purpose here was to create, by completing the square, this trinomial, which I knew from the beginning, because of the way I constructed it, would turn into this binomial squared. The number that you put into your binomial squared, let's make a different color, right here, is always going to be the same as your p over 2. It's going to be your p over 2. Scratch that. I made a mistake. It's not your p over 2. It's your p. It is your b over 2. It's always going to be your b over 2, because that's the number, when you FOIL this out, it's going to give you as your last term your 9/4. 3 halves, when you FOIL x plus 3 halves out, let's just do it. My first, x squared. My second, my outer, plus 3 halves x. My inner, another plus 3 halves x. My outer, plus 9/4. And always and forever, you've done plus, because you've squared it. You've got 3 halves x plus 3 halves x. I'm adding those two together. I am doubling it. So I am at x squared plus 3x plus 9/4. Once again, that's the same thing that I had right up here when I was starting out to complete the square. So now that I've completed the square, once I've gotten to this wonderful part here, let's see if I can't segment that out here. That works. I think it's going to call too many things in, but let's try it. Let's copy that. Let's see if we can't bring it to the bottom. Come on, go away. I want to go away. Come on, come on, come on. I'm wasting my time. There we go, that's better. Let's erase some of this stuff here. Sorry. Erase that little smile. Scoreboard is getting upset with me. Okay, so let's just finish this problem up. Now it's pretty easy. This is now turned into x plus 3/2 squared is equal to, well, let's call this 28/4 plus 9/4. So it's equal to 37/4 x plus 3/2 squared. Let's take the square root of both sides. Don't forget your plus or minus. I end up on this side here with x plus 3/2. And on this side here, I have radical 37 over radical 4. So I have x plus 3/2 is equal to radical 37 over 2. Let's subtract 3/2 from both sides. I am left with x is equal to negative 3/2 plus or minus radical 37 over 2. So I can just write that a little bit easier. X is equal to negative 3 plus or minus radical 37 over 2. One more thing I'll point out about this. Let's go back to our original equation. Press that, paste it, I said, there we go. Okay, here's our original equation. And I'm going to change this plus to a minus. So remember, I want to get this into a form of x plus p squared. And my p is going to be equal to b over 2. My b over 2, in this case, is negative 3 over 2, because my b is now a negative. But when I square that to get my c, my new c, it's still going to be plus 9/4. So let's take the original equation again. I have x squared minus 3x plus blank is equal to 7 plus blank. I've already determined that my b over 2 squared right here is equal to positive 9/4. That's why this is always going to be plus blank. It's always going to be plus blank. It's never going to be minus blank. But now, when I make this into my binomial squared, I have x minus 3/2 squared is equal to 7 plus 9 over 4. Minus 3/2 right here. This is my p that I was doing, and it happened to be negative. So it's always going to be the same sign in here as the number that you're squaring. But what you end up with when you square it, whether it's a negative or a positive number, is always going to be positive. Well, I hope this helps you grok a little bit of what it means to complete the square. One final thing. I may as well just have one final thing. We've done this before, but if you actually took ax squared plus bx plus c equals 0 and tried to solve for x by completing the square, you're going to wind up with negative b plus or minus square root of b squared minus 4ac all over 2a. It's a good exercise to do. But what this is telling me is that the quadratic formula is really only a shortcut for completing the square. And that the two ways to solve a quadratic equation are completing the square, which is the normal way that you would do it, because the only other way is factoring, and factoring only happens in very rare circumstances.